An estimated 100 million tons of plastic are produced each year, with approximately 10% ending up in the world's oceans. Areas such as the North Pacific Gyre, often referred to as the North Pacific Garbage Patch, now contain 6 parts plastic to 1 part plankton, transforming the world's largest ecosystem into a toxic plastic soup. Patrick Filotti, founder of the Global Mana Foundation, is on a mission to save the oceans. So he went to meet the man who discovered the North Pacific Gyre and first sounded the alarm about plastic pollution in the oceans.
Charles Moore, I'm the captain of the oceanographic research vessel Algeta and the founder of the Algalita Marine Research Foundation and Long Beach Organic. What I actually discovered was that I was passing through a part of the ocean that was littered, but it was littered sporadically. It wasn't littered as like an island of trash. It was just sporadic pieces of litter. But the point was, for an entire week, I couldn't come on deck without seeing some of this litter. And this is as far from human civilization as you can get anywhere on Earth. So I began looking at weather maps and weather faxes and seeing how this high generally hugged this area, and created a hypothesis that maybe the fact that there's so much trash here had to do with this weather system, this high pressure system. So I went back 2 years later and was able to characterize this area where I had been by going first east to west and then north to south, sort of into the center of a circle and then out to the edge again. Took those samples back to the lab and analyzed them and found to our shock that there was 6 times as much plastic by weight as actual zooplankton in this area, the natural food that fish are feeding on. It's so dispersed it's very difficult to assess it in any meaningful way on a single cruise. What we do know is that the longer it stays in the water, the more polluted it's going to get, because plastics floating in the water, in addition to breaking down into small bits, accumulate pollutants. So they're sponges for poisons and then transmit those poisons to the food web. So every additional piece of plastic we put in the ocean is a potential poison pill to the creatures that live in the ocean.
Patrick stopped in at the Algalita Research Facility in Long Beach, California, to take a closer look at the samples collected by Captain Moore and his team on their expeditions to the gyre.
My name is Gwen Latin, Director of Laboratory Research. I study plastics in the environment. Most people aren't aware of just how much plastic is in the environment, and that's one of the things we're trying to document. There's floating plastics or sinking plastics. Depending on the weight and the density of the plastic, they can either float or they can sink. So they end up everywhere in the environment, not just floating in the water column, but on the bottom. There are all different sizes of plastic. And with the natural sand and the rocks. And this right here is kind of the 2.8 millimeter size. This is a 1 millimeter size. And you can still see all the different bits and pieces of plastic that are there in with the sand. Even as you go down to the smaller sizes, yes, you have a lot of sand, but you can see all the different colored and different pieces of plastic that are in that sand. Even as you get down to the 0.5 millimeter size range, in with the sand, there's a lot of different types of plastic. And when it goes even down to 1/3 of a millimeter, there's plastic in that. And it even goes finer than that. But when we get down to this size, when we sieve it out, we end up with different types of plastic that are floating right in the water that you can barely see.
So humankind is changing the composition of the earth and the seawater with plastic since it doesn't biodegrade.
Having met with Captain Moore and equipped with a sample courtesy of the Algalita Marine Research Foundation, Patrick traveled to Salt Lake City, Utah to meet with Bob Herbst, the founder of H2O Technologies, and conduct an experiment.
I've been working with electro coagulation technology for over 30 years. I have 11 patents on the process, and it's particularly a good technology for removing things like we're talking about here, for particles and suspended solids in water. We've treated many different waste streams, mine drainage, oil fields from drilling the wells, to the produced water that comes up as the oil and gas is being produced. We actually took oil field water from 10,000 parts per million and we took it down to less than 100 parts per billion.
So this actually is plastic gathered from the North Pacific Gyre, and Algalita Research was happy to let us use this for our experiment. This is our control sample here. We're going to send this to the lab afterwards, but this actually is our experiment.
What we're going to do here is we're going to put in the electrode, and then we will add current to this, sufficient current density for our electrochemical reaction to start happening. See here on the sides, the fluid is being pulled in between the two electrode blades. As it's pulled in there, there's electrons that are traveling from one electrode to the other that are going into those particles, and they're making the particles very electronegative. This will cause them to become dense and heavier, and ultimately they will start settling out. Initially here we're going to get floating material that's going to come up because of the hydrogen and oxygen bubbles that are coming up. These particles have an affinity particularly for the hydrogen bubbles because they're electropositive, and they will hold this up until the bubbles break and release. Once that's done, the density of the material will cause it to sink. There's also metallic particles that are being crystallized in there and becoming very heavy and dense, and they are settling right to the bottom. What we did here was we used an iron electrode to help take other contaminants out of there that might have been in there. Polished it with an aluminum electrode. That should give us better clarity of water, and it's definitely giving us better metal removal. There's a number of the metal oxide crystals in there that are sinking fairly rapidly. This is the two samples. This is the raw sample, and you can see these suspended particles in there that are not settling out. This is the sample that's after electrocoagulation and decanting off the clear water.